To create this 180-ton finished turbine, we begin with 130-ton steel forging and the first cut. This single forging will become the low-pressure rotor, the heart of the world's most powerful carrier engine. The lift capacity and safety protocols required for a 130-ton single lift. Before any metal is removed, every millimeter of this 130-ton ingot is scanned for defects that could destroy the engine at sea. The exact alloy and traceability chain required for naval nuclear service. The first cut will remove 8 tons of scale and establish the true centerline that must hold to 10 microns for the next 18 months of machining. One micron error now becomes 10 microns later, and 10 microns at 3600 RPM is catastrophic. The bulk shaping is complete. Now the rotor enters the phase where every cut must hold to 5 microns. A misalignment of even 10 microns here will become a 0.3 millimeter runout at the blade tips, enough to destroy the engine in minutes. Each of the 7 grooves must be identical to within 4 microns is exactly the same centrifugal load. This single groove will hold 92 blades. Every measurement taken here decides whether the engine will run for 50 years or fail in the first month at sea. This groove alone must survive 30 million stress cycles. The finish you see here is what prevents fretting and crack initiation. The precise angular spacing required for balanced steam flow across all 7 stages. Every groove must be identical. Any variation between them creates an imbalance that balancing cannot fully correct. A single undetected flaw in any groove root would grow under cyclic stress until the blade flew out at there can survive. 7 perfect grooves now exist where once there was only solid steel. The rotor is ready for its blades. Different blade heights and twist angles match to the steam expansion profile. A single gram difference in blade weight at the tip creates an imbalance that must be corrected later with tiny balance weights. This single blade will experience 12 tons of centrifugal pull at full speed. It must seat perfectly or the entire stage fails. The dual locking system, fir tree geometry plus mechanical pin, required for carrier reliability. Each blade is moment weighed before installation so heavy and light blades can be alternated around the circumference. Platform gaps must be held to 0.15 millimeter to control steam leakage and vibration. Stage 1 is complete. 92 blades now spin as one, their combined mass adding 1.8 tons to the rotor. Alternating heavy and light blades across stages avoids harmonic resonance. These wires and shrouds, essential for surviving the turbulent steam flow inside a carrier turbine. 644 blades, the Rosic fir tree wheel. This final inspection catches what balancing cannot. A single loose blade would destroy the engine at sea. The multi-plane balancing approach required for a rotor longer than 11 meter with 7 distinct mass centers. Even before it reaches operating speed, the machine measures the rotor's true mechanical centerline to 0.5 μm. At only 500 RPM, the unbalance already equals the weight of a small car. This is why every gram matters. The classic influence coefficient method used on every large marine turbine rotor. The machine has just solved a 16-variable equation in 4 seconds, something that once took engineers days with slide rules. These 3 small weights will keep 128 tons of steel and 644 blades running smoothly for the next 50 years. Higher speed reveals different deflection modes that single-plane balancing cannot address. At 3000 RPM, the rotor is already experiencing 70% of its full centrifugal load. The last grams are added with watchmaker precision. 0.28 mils at this is the moment the engine earns its right to power an aircraft carrier. The rotor is now certified for installation in the world's most powerful carrier engines. Every gram added, every angle recorded, this rotor's balance history will travel with it for the next half-century. Balanced to naval standards, the rotor now leaves the balancing cell for the final assembly of the complete turbine. One last look. 644 blades, 7 grooves, 2 planes of balance weights, all verified. The rotor that was born from a 130-ton forging now sits inside the casing that will protect it for the next 50 years at sea. Diaphragms convert pressure energy into velocity before the moving blades extract it to the rotor within 0.3 millimeter, or efficiency drops and vibration rises. 7 diaphragms and 644 moving blades now form the complete steam path. The turbine is ready to be closed. Every critical parameter is now monitored. The engine will tell the crew if anything is wrong before it becomes dangerous. One final look inside. 644 blades, 7 diaphragms, 2 bearings, everything exactly where it must be. The casing is now a single pressure vessel. It will hold 600 psi steam at 500 degrees C while the ship fights 30 knot seas. The engine that will push a 100,000-ton carrier at over 30 knots is now complete. Before this engine can power an aircraft carrier, it must prove itself here, under full load, full speed, and full scrutiny. Every sensor that will protect this engine at sea is tested here first. One faulty reading and the test stops. At 3,000 RPM, the rotor is experiencing 70% of its hull vehicle. 3,600 revolutions per minute. The rotor that began as a 130-ton forging now spins 26 megawatts, enough to push a 100,000-ton carrier at over 30 knots. 4 hours at full power with zero drift. This is the proof the Navy demands before any engine is allowed aboard a carrier. A carrier can lose a propeller shaft in combat. This engine must survive that moment without overspeeding or failing. All parameters confirmed against naval specification.
Agreed. The numbers are...
This engine is ready to leave the factory. Tested to naval standards and preserved for its journey, the engine now begins the last leg of its factory life. One last inspection. Every seal, every tarp, every gram of preservative must survive the journey to the carrier's engine room. Every cut, every balance weight, every test result travels with this engine. The Navy will know its full history before it ever turns a propeller. Not a single blade shows distress. Not a single diaphragm has shifted. The precision we watched from the first forging is held. Raw forging to tested, preserved, and delivered here into this journey, it is ready to power history. After its protected journey, the engine is revealed exactly as it left the test cell, perfect and ready for its place in history. The engine that began as a 130-ton forging is about to take its place inside the most powerful warship ever built. Lowered into the heart of the carrier, this engine will soon push 100,000 tons through the ocean at more than 30 knots. Every micron of alignment here determines whether the engine will run smoothly for 50 years or shake the carrier apart. These vibrations will force wrestler and the shock of combat. They will never move again. For the first time, the engine that was built in the factory turns inside the ship it was made for. The build is complete. Steam from the carrier's reactors now drives the engine that was built to receive it. The loop is closed. Protected inside its steel home, the engine waits for the moment the carrier slips into the ocean and proves its power. At 15 knots, the engine is already proving itself in the real world. Salt air, rolling seas, and the full weight of naval responsibility. 25 knots and 18 megawatts. The engine is already doing what it was built to do. 31.5 knots. The engine that don't run in warship.
4 hours at full power in the open ocean. The engine has now earned its place in naval history.
The world's most powerful aircraft carrier engine is now ready to serve. After pushing the carrier at full power for days, the engine is opened one last time. It is perfect. Sealed and ready, this engine will now serve for the next 50 years, the quiet heart of the world's most powerful warship. The engine that was built from raw steel is now part of a ship that will carry the flag of the United States across every ocean. From 130-ton forging to this is how the world's most powerful aircraft carrier engines are built. Even after commissioning, the engine receives one final verification. The Navy leaves nothing to chance. The engine that was built with such precision is now entrusted to the men and women who will keep it running for the next 50 years. Ready for deployment, this engine will soon sail into harm's way, the ultimate test of everything that was built into it. Day after day, this engine will run quietly and reliably. After a month at sea, the engine is opened for its first routine maintenance. It is as perfect as the day it left the factory. While aircraft launch and recover above, this engine runs without pause, the quiet foundation of every mission. "90 days at sea, not a single issue. The engine that was built with such care is now proving its worth every single day. Even in the middle of a deployment, the engine receives the care it deserves, because the carrier depends on it. Home from its first deployment, the engine has proven itself in the real world, exactly as it was built to do. The story of this engine, from the first cut on 130-ton forging to its first deployment, is now part of naval history.